Hey guys, Reed here. Today we're going to have a very interesting conversation about lithium, right? Lithium is an amazing medication. It's one of those medications that have has a bad rep, but it's used so many times and it's used in some of the most complicated cases. But lithium is an amazing medication, and I think you should know the mechanism of it so you can see how much benefit it can have. Now, lithium is an anti-manic medication. It's an anti-manic agent, and lithium is an ion. It's not a compound, so it doesn't need to be metabolized. It simply needs to be secreted, like lithium, salt, sodium, potassium, all of those. Right. So lithium plays a very important role with augmentation. Like if you have a patient that's on your, let's say you have a patient who's you're treating for depression, and you have the person on an SSRI. You start the person on the SSRI, and you get a little response. You increase it, you may get a little bit more response. You increase it more to the maximum, something like that. You may not get as much of a response. What do you do there? Well, you want to see about using lithium. May consider using lithium in that circumcision situation as an augmentation strategy, right? And the reason why is this. Let me show you. Let me sort of show you how this sort of works. Okay. Okay. What I'm looking for. I'm looking for. Let me give you an image of the um, image of synaptic cleft. Okay. Let's see. Let me pull up this one here. Okay. Okay. Here's the presynaptic neuron right here. Here's the postsynaptic neuron right here. Presynaptic, postsynaptic. Okay. Now, here, okay, great. Here, the ligand is binding the receptor. And after the ligand binds the receptor, then there's a 3D configuration change in the receptor, right? And that leads to the signal transduction cascade that sends the message to the cell body on what we want what this ligand here, this molecule is intending to have the cell produce. So this molecule is binding to the receptor to translate a signal to the cell body to produce more of X, right? In the situation that I described where the person is on an antidepressant or something like that, and we have basically all the receptors bound, but there's no response, it could be that the signal transduction cascade, the inner signal, is malfunctioning, right? So we can not only get one, so we think that once the ligand is bound to the receptor and when the receptor is activated, we think that we're going to get a response for the cell. But what happens is the mechanism that transfers the signal could be disrupted, and that's what lithium is for, right? So you're giving someone medications and the receptors are not working. So you give them lithium. Lithium works on that signal transduction cascade after the reception. And that's what we're going after the receptor. And this is what we're going to look at the signal transduction here. I hope you got that. Okay. So let's look here. Let me see. Okay, explain the signal transduction cascade when ligands bind G protein receptors. Okay, here's the signal transduction cascade. Let me see if before I go here, let me just try to pull up an image of the signal transduction cascade so you know what I'm talking about. Signal transduction cascade, let me see here. Okay, well, Man, they doing this in Khan Academy? Okay, here. All right, and so here are here's example here. Here's this. This is the postsynaptic receptor. It could be the presynaptic receptor, but here are the ligands. Right, they're binding the proteins, and this is resulting in a series of reactions that release two subunits, and those subunits become active and start doing here. But I never remember. I have to go back and always remember the things here. But but you can see what's happening here. Oh, okay. So this is interesting that this, I never, somehow, I never placed the signal transduction cascade within the plasma membrane. I thought it was inside the, okay, no, oh no, this is the nucleus. Okay, yeah, okay. No, here's the, it is, right, it's the plasma membrane here, here's the cell, this is the nucleus here. So here's the receptors. This is the signal transduction cascade that go ahead and sends the signal here, phosphorylation. So let me go ahead and go through this. I think I have a better example than this one. But you see what I'm saying? This, when you can get to a certain point where this pathway isn't really working well, and this is one of the reasons why you want to sort of use lithium. Look, here's the signal here. Here's the receptor. Here's the conformational. It starts off with this, then it's conforming to this, then it's conforming to that, and then it's going to send this message to the cell body, and the cell body is going to produce something and then have it exported out of the cell body. So this is a signal transduction pathway I'm talking about. I don't think it's very necessary to get into. I don't even remember all the, I look at it for years and everything, just don't stick to memory. But this is the pathway here, and this is what you want to use lithium to sort of help work on if you are not getting a good response. Okay, so I think I got that. Okay, here, explain the signal transduction cascade when ligand binds G protein receptors. Excellent questions. Let's break down the signal transduction cascade that occurs when a ligand binds to G protein couple receptors. Now, I specifically put G protein couple receptors, not ionotropic receptors that turn on and off. Like those gate controlled and ionic controlled, not those. Those just turn on and off and deal with the currents that's coming across to maintain that action potential, right? But I'm talking about the G proteins that are there to take the signal so that you can produce things from the cell. Okay, so my search was specifically for those. G protein couple receptors are membrane proteins that convert extracellular signals like hormones or neurotransmitters into intracellular signals via G proteins and second messages. You got me now? Right. The key steps are the ligand binds to the G protein receptor. The G protein receptor activates a G protein, right? So you have the G protein receptors, and it has two subunits that are inactive when it's bound to it. The configurational change results in release of the two subunits, and they go on and start doing their thing, right? Okay, so G protein activates or inhibit an effector enzyme or channels. Right, okay, yeah, see, the G protein can turn off or turn on these ligand-gated or ion channels, right? Ion channels here. And then also, this signal transduction cascade typically results in the cell producing something that's going to be exported out for the cell's functioning, right? Then you get a cellular response, then the signal is terminated. Okay, those are the steps. So here, that's step one. Step two, receptor ligand binding. The ligand signal molecules such as epinephrine, dopamine, serotonin, or acetylcholine bind to extracellular domain of the G protein. Okay, the ligand binds. The receptor changes shape. That means there's a conformational change. The conformational shifts alters the cytoplasmic side of the receptor, allowing it to interact with a nearby heterometric meric G protein. Yep. Let me show you this. Let's go this again. The conformational shift alters the cytoplasmic side of the receptor. So remember, the ligand is on the extracellular. It binds to the extracellular domain, right? And then the conformation alters the cytoplasmic side of the receptor, allowing it to interact with their nearby heterometric G protein, right? Okay. Activation of the G protein. G proteins are heterotrimers with three subunits after alpha, beta, gamma. Okay. In the inactive state, the alpha subunit is bound to GDP. When the GRAC protein is activated, it acts as a G guanine nucleotide exchange factor, causing the alpha unit to exchange GDP with GTP for GTP. This activates the G protein. The alpha subunit dissociated from the beta dimer, and both can signal independently. This is the G protein right here, activation. Yeah, look, effector activation. Yep. The active G alpha or the gamma or beta complex interacts with downstream effector proteins such as GS stimulatory, G inhibitory, phospholipase, these channels. Okay. Second messenger generation. Effector enzymes create second messengers which amplify the signal. Effector enzymes create second messengers, right? So if you have a ligand that's going to activate the receptor, then these second messengers is going to amplify the signal what they want. Adenylate cyclase produces CMP, which activates protein kinase A. Phospholipase C splits into PIP2. PIP3 phosphoinositol triphosphate triggers calcium release from the endoplasmic reticulum. DAG, what was it? DAG activates protein kinase C, and then ion channels alter membrane potential and carry and calcium entry. Next, you also have a cellular response. Activates kinases, phosphorylate target proteins. I'm sorry. Okay, let me slow down. Okay, here. Okay, this is the second messenger generation. Okay, and then here's how the cell responds. Activated kinases, such as phosphorylate target proteins, the kinases phosphorylate target proteins, and this alters the enzyme activities. Again, gene transcription, yeah, ion channel conductions, and the cellular metabolism, secretion, or contraction, etc. Now, see, 6 is the point where the cell actually responds. So with all of these kinases activated, you get phosphorylation of all of those target proteins. And as a result, it results in a change in enzyme activity, a change in gene transcription. These are the new genes that we want to have expressed. A change in ion channel conductance, meaning changing the action potential. And this results in metabolizing, producing, and taking in other substances from the cell. Okay. Next, signal transformation. To prevent overactivation, the G alpha subunit hydrolyzes GTP to GDP. And via intrinsic GTPase activity, also is often accelerated by RGS proteins. Right. Okay. So the alpha subunit has an intrinsic GDPase activity, and so therefore, it's going when it's released, it's going to convert GTP to GDP and therefore deactivate itself. Alpha GDP reassociates with the gamma and it activates the G protein, right? So that gamma subunit has has intrinsic GTPase activity, and therefore, when the alpha subunit is released, there's only a matter of time before it cleaves the bond between GTP to GDP, and therefore it causes a reassociation between the alpha and gamma subunits, and then therefore we have the inactivation of the G protein. Got me? Next, receptor desensitization via GRK and B arrestin, which prevents further coupling. Hold on one second, guys. Okay, let me see here. Okay, where we at? Okay, and so here's how the signal is terminated. I think that's all we have for today. I think that's really what reason I wanted to sort of use lithium. Okay, I hope that's clear for you guys. Okay, let's see here, and then let me know if you guys have any questions. Again, if you do, it's a pleasure. Otherwise, I'll talk to you guys later. Okay, take care, guys. Take care, guys.